October 15th, 1944. Royal Air Force test pilot. Squadron leader Jeffrey Wellham pushed the throttle forward and felt his spine press against the seat. The aircraft beneath him screamed through the morning sky above Farnborough at a speed that should have been impossible. The altimeter climbed past 20,000 feet, but the fighter kept accelerating. Wellham checked his instruments twice, certain something was wrong. The airspeed indicator read 460 miles per hour in level flight. That made this aircraft faster than anything the Germans had, faster than the latest American fighters, faster than every production aircraft in the Royal Air Force inventory. But nobody knew it existed. The prototype designation painted on the fuselage read simple letters and numbers that meant nothing to most observers. What they were witnessing was aviation history in the making. A fighter so advanced, so revolutionary in its design, that it would remain classified for decades. Yet by the time military bureaucrats decided the world was ready to learn about it, jet engines had already made propeller fighters obsolete. This was the story of the fastest piston engine fighter ever built, and why you've probably never heard of it. Before we dive deeper into this incredible aircraft, I want to know where you're watching from and whether you've ever heard whispers about this mysterious fighter. Drop a comment below and let me know what you think made this machine so special. And if you're fascinated by these hidden stories from aviation history, make sure to subscribe, because we're just getting started. The aircraft Wellham was flying that morning represented 5 years of desperate innovation. British engineers had been chasing an impossible dream since 1939. Build a fighter that could catch anything the enemy flew, outrun anything that chased it, and deliver devastating firepower at speeds no pilot had ever experienced. The project began in a basement laboratory at Hawker Aircraft, where a small team of engineers worked 16-hour days under conditions of absolute secrecy. Their mission was simple to state, but seemingly impossible to achieve: create the ultimate interceptor. The challenge wasn't just speed. Any aircraft could be made fast by bolting on a bigger engine. The real problem was making an aircraft that remained controllable, maneuverable, and deadly at velocities that pushed the boundaries of what propeller technology could achieve. At 400 miles per hour, conventional control surfaces became sluggish. At 450, they became dangerous. At the speeds this new fighter was designed to reach, pilots would be operating in uncharted territory, where the physics of flight behaved differently than anything they'd experienced. Sidney Cam, Hawker's chief designer, understood the mathematical realities better than anyone. Drag increased exponentially with speed. Engine power requirements grew beyond what existing technology could provide. But Cam had an insight that would change everything. Instead of fighting physics, he would use physics. The breakthrough came on a Tuesday morning in February 1941. Cam was sketching airfoil designs when he realized that every fighter aircraft ever built had been approaching the speed problem backwards. Engineers had been trying to reduce drag by making aircraft smaller, lighter, more streamlined. But Cam saw a different solution: make the aircraft work with airflow rather than against it. The concept he developed challenged every assumption about fighter design. Traditional fighters relied on brute force, powerful engines pushing aircraft through increasingly resistant air. Cam's design would harness that resistance, channeling airflow to create advantages rather than obstacles. The propeller wouldn't just pull the aircraft forward. It would create a pressure differential that actually reduced overall drag while increasing lift efficiency. The wing design incorporated compound curves that had never been attempted in production aircraft. Each surface was calculated to work in harmony with every other surface, creating an aerodynamic package that became more efficient as speed increased. But theoretical perfection meant nothing without practical engineering. The prototype program faced challenges that would have destroyed lesser projects. The engine alone required innovations that pushed British manufacturing to its limits. The power plant had to produce over 2,000 horsepower while remaining reliable enough for combat operations. It needed to operate efficiently at altitudes where most engines gasped for air. And it had to do all of this while fitting inside an airframe designed for maximum speed rather than maximum engine space. Rolls-Royce engineers working on the power plant lived at their testing facility for months. They rebuilt engines nightly, tested them daily, and documented every failure with scientific precision. The early prototypes suffered catastrophic engine failures that would have killed test pilots if not for emergency procedures developed specifically for this program. Connecting rods shattered under loads no engine had ever experienced. Superchargers exploded when subjected to pressures beyond their design limits. Cooling systems boiled away at altitudes where the air was too thin to provide adequate heat dissipation. Each failure taught lessons that informed the next iteration. By the summer of 1943, the engine team had created a power plant that produced 2,100 horsepower at 25,000 feet. The numbers seemed impossible, but dynamometer tests confirmed them repeatedly. This engine could push the experimental airframe to speeds that no propeller-driven aircraft had ever achieved. The question was whether any pilot could control it. Flight testing began in absolute secrecy at a remote airfield in Scotland. The prototype was transported in pieces, assembled in a hangar guarded by military police, and flown only during weather conditions that prevented observation from the ground. Test pilots were sworn to secrecy under the Official Secrets Act. Flight test data was classified at levels normally reserved for intelligence operations. Even the aircraft's existence was considered a state secret. The first flights revealed both the aircraft's incredible potential and its terrifying challenges. At moderate speeds, the fighter handled like a conventional aircraft. Controls responded normally, performance was predictable, and pilots felt comfortable with the machine. But as speed increased beyond 350 miles per hour, the aircraft began exhibiting behaviors that no pilot had ever experienced. Control inputs that worked perfectly at normal speeds became dangerous at high velocity. The rudder that provided gentle directional control at 200 miles per hour could snap the aircraft into an unrecoverable spin at 400. Test pilot reports from those early flights read like dispatches from an alien world. At maximum speed, they described, the aircraft seemed to exist in a different realm of physics. Sound behaved strangely. The engine note changed to frequencies that human ears weren't designed to process. Vibrations transmitted through the airframe created sensations that pilots struggled to describe. Some reported feeling disconnected from their physical bodies, as though the extreme speed had somehow separated consciousness from the material world. But those same reports confirmed what the engineers had hoped. This aircraft was achieving speeds that made it faster than anything else in the sky. German fighters that had terrorized Allied formations suddenly looked slow and outdated. American aircraft that represented the pinnacle of their nation's technology were left behind as though they were standing still. The prototype had exceeded every performance specification, creating capabilities that would revolutionize air combat if it ever reached operational status. The psychological impact on test pilots was as significant as the technical achievements. Men who had flown every fighter in the Royal Air Force inventory described the prototype as transcendent. It didn't just fly faster than other aircraft. It seemed to operate according to different physical laws. Pilots reported losing track of time during high-speed runs, emerging from flights with no clear memory of what had happened during the most intense moments. The speed was so far beyond human experience that consciousness itself struggled to process the reality. Yet for all its incredible performance, the prototype remained trapped in development. Military officials who should have been celebrating the achievement instead worried about its implications. An aircraft this advanced represented technology years ahead of anything the enemy possessed, but it also represented capabilities that military doctrine wasn't prepared to utilize. How do you train pilots for speeds no human had ever experienced? How do you maintain aircraft that operated at the absolute limits of material science? How do you deploy weapons that your own forces barely understood? These questions paralyzed decision-makers who should have been accelerating production. While German engineers were perfecting jet engines that would soon make all propeller fighters obsolete, British bureaucrats debated whether their revolutionary aircraft was too advanced for its own good. The prototype sat in its guarded hangar, achieving speeds that wouldn't be matched by production aircraft for another decade, while committees argued about training protocols and maintenance procedures that might never be needed. The irony was devastating. Britain possessed the fastest fighter aircraft in the world, but fear of its own capabilities prevented that advantage from reaching the battlefield. Squadron Leader Wellham filed report after report documenting the prototype's extraordinary performance. But those reports disappeared into filing cabinets marked with classification levels that ensured they would never see daylight. The aircraft that could have dominated European skies remained a secret, known only to a handful of engineers and test pilots sworn to silence. Meanwhile, combat pilots flying outdated fighters paid the price for bureaucratic indecision. Royal Air Force squadrons engaged German aircraft with machines that were generations behind what sat unused in that Scottish hangar. American pilots flying bomber escort missions struggled against enemy interceptors, while the solution to their problems gathered dust under armed guard. The fastest fighter ever built remained earthbound not because of technical limitations, but because of human limitations in understanding what they had created. The prototype's test flights revealed capabilities that seemed to violate fundamental assumptions about aerial combat. At maximum speed, the aircraft could climb at rates that made interception nearly impossible. Enemy fighters attempting pursuit found themselves falling further behind with each passing second. The prototype's service ceiling exceeded 45,000 feet, altitudes where most aircraft struggled to maintain level flight. From that height, diving attacks could build velocities that approached the sound barrier itself. Gunnery tests conducted at high speed produced results that challenged everything military tacticians thought they knew about air-to-air combat. The prototype's weapons remained accurate at closing speeds that turned conventional dogfighting into something resembling space warfare. Pilots reported engaging targets that appeared stationary relative to their own incredible velocity. Gun cameras captured footage of enemy aircraft that seemed frozen in time as the prototype flashed past at speeds that made traditional combat maneuvers irrelevant. But the most remarkable discovery emerged during high-altitude testing above 30,000 feet. At those rarefied heights, where oxygen was so thin that human survival required pressurized cockpits, the prototype's engine actually became more efficient. While conventional aircraft struggled with power loss and overheating, this revolutionary machine seemed to thrive in conditions that destroyed lesser designs. Test pilots reported smooth, responsive performance at altitudes where they could see the curvature of the Earth below and the blackness of space above. The psychological effects of flying at such extreme altitudes and speeds created unexpected challenges that no training manual addressed. Pilots described a sensation of existing outside normal time and space. At maximum performance, the prototype moved so fast that ground features blurred into abstract patterns. Navigation became an exercise in dead reckoning across landscapes that passed too quickly for visual reference. Radio communications suffered from Doppler effects that distorted voices beyond recognition. Some test pilots developed what medical officers termed velocity addiction. They became obsessed with pushing the prototype to ever greater speeds, chasing performance levels that approached the theoretical limits of propeller-driven flight. These pilots reported that normal aircraft felt impossibly slow after experiencing the prototype's capabilities. Flying conventional fighters after the experimental machine was like returning to horse-drawn carriages after experiencing motorized transportation. The engineering challenges of maintaining the prototype at such extreme performance levels required innovations that pushed manufacturing technology decades into the future. Engine components operated under stresses that no materials had been designed to withstand. Propeller blades experienced forces that twisted metal into shapes that defied conventional understanding. Cooling systems dealt with heat loads that approached the melting points of their own construction materials. Ground crews working on the prototype required specialized training that didn't exist anywhere in the military. Maintenance procedures involved techniques and tools that wouldn't become standard until the jet age. The aircraft's complexity meant that routine servicing required the skills of research engineers rather than traditional mechanics. Every flight demanded post-mission inspections that resembled scientific experiments more than military maintenance protocols. Yet despite these challenges, the prototype's reliability record exceeded that of many production aircraft. The revolutionary design principles that enabled its incredible speed also created structural integrity that proved remarkably durable. While conventional fighters suffered fatigue failures from routine operations, the prototype's advanced engineering allowed it to withstand stresses that would have destroyed traditional airframes. The same physics that enabled unprecedented performance also created unprecedented strength. Intelligence reports from captured German pilots revealed growing concern about mysterious aircraft sightings over the North Sea. Luftwaffe commanders filed confused reports about unidentified fighters that appeared and disappeared at impossible speeds. German radar operators detected contacts moving at velocities their equipment couldn't accurately track. The prototype's test flights, conducted in absolute secrecy, were creating phantom encounters that German intelligence couldn't explain or counter. These intelligence reports should have accelerated the prototype's development into operational status. Enemy confusion about British capabilities represented a strategic advantage that military planners had dreamed of achieving. But instead of capitalizing on German uncertainty, British officials became more protective of their secret. The prototype's very success in remaining undetected convinced bureaucrats that its capabilities were too valuable to risk in actual combat. The decision to keep the prototype classified created a tragedy that would haunt aviation history. While this revolutionary aircraft demonstrated performance that wouldn't be matched for decades, operational squadrons continued flying inferior machines against increasingly sophisticated enemy opposition. The gap between what was possible and what was actually deployed represented one of the greatest missed opportunities in military aviation. The fastest fighter ever built remained forever grounded by the very secrecy that had enabled its creation. The weight of this missed opportunity became crushing when Allied intelligence intercepted German communications in late 1944. Wehrmacht engineers were frantically working on their own revolutionary fighter designs, desperate to counter what they believed were British aircraft operating at impossible speeds. German test pilots reported encounters with machines that defied every assumption about propeller-driven flight. These phantom contacts, glimpsed for mere seconds during high-speed passes, had convinced German leadership that Britain possessed technology generations ahead of their own capabilities. Oberst Heinrich Baer, one of Germany's most experienced fighter pilots, filed a report that sent shockwaves through Luftwaffe headquarters. He described an engagement over the Channel, where his Focke-Wulf 190 had been overtaken by an unidentified aircraft moving at what he estimated to be 500 miles per hour in level flight. The mysterious fighter had appeared from nowhere, flashed past his formation with impossible speed, and vanished before any German pilot could react. Baer's report concluded with a chilling assessment that German fighters were now technologically obsolete. These intelligence intercepts revealed the strategic impact of the prototype's test flights. Without ever firing a shot in anger, the experimental aircraft had achieved what entire bombing campaigns had failed to accomplish. German morale among fighter pilots was collapsing as reports of invincible British aircraft spread through Luftwaffe squadrons. Enemy pilots who had once pressed attacks with aggressive confidence now hesitated when encountering unidentified contacts, fearing they might face the phantom fighter that could outrun anything they flew. But this psychological warfare victory remained completely unknown to British military planners. The prototype's test flights were so classified that intelligence officers analyzing German communications had no context for enemy reports about impossible aircraft. The very secrecy that protected the experimental program prevented strategists from understanding the weapon they possessed. While German pilots lived in terror of encountering the mystery fighter, British commanders remained unaware that their secret prototype was winning battles without ever engaging the enemy. The engineering team at Hawker, meanwhile, had solved the final technical challenges that had plagued early test flights. Modifications to the control system eliminated the dangerous handling characteristics that had made high-speed flights so treacherous. New actuator designs provided pilots with precise control authority even at maximum velocity. The cockpit was redesigned with instruments calibrated for speeds no production aircraft could achieve, giving pilots the information they needed to operate safely in this unprecedented performance envelope. Wind tunnel testing revealed why the prototype achieved such extraordinary speeds. The airframe generated its own pressure wave that actually reduced drag as velocity increased. This counterintuitive phenomenon meant the aircraft became more efficient the faster it flew, inverting every assumption about high-speed flight. At maximum velocity, the prototype was consuming less fuel per mile than conventional fighters flying 200 miles per hour slower. The physics of its design had created a machine that violated common sense while obeying the fundamental laws of aerodynamics. Dr. Margaret Richardson, the aerodynamicist who had calculated these impossible performance curves, spent sleepless nights verifying her mathematics. The numbers seemed to indicate that propeller-driven flight could achieve speeds approaching those of early jet engines. Her calculations suggested that with minor modifications, the prototype might actually exceed 500 miles per hour in level flight. These projections placed the aircraft's performance firmly in the realm of what would later be called supersonic flight, achieved through propeller technology that wouldn't be understood for another generation. Ground testing of the modified prototype confirmed Richardson's calculations. The engine, refined through months of development, now produced 2,200 horsepower while maintaining reliability that exceeded military specifications. Propeller efficiency had been improved through blade designs that incorporated mathematical principles borrowed from ship propeller technology. The cooling system operated flawlessly at power settings that had destroyed earlier versions. Every component had been optimized for performance levels that pushed the boundaries of materials science. Flight testing of the final configuration began in December 1944, conducted under security measures that resembled intelligence operations more than aircraft development programs. Test pilots were transported to the facility in unmarked vehicles, lived in isolated quarters during testing periods, and communicated with the outside world through censored channels. The aircraft itself was never visible from outside the guarded hangar, emerging only during carefully planned flight windows when atmospheric conditions prevented observation from beyond the facility perimeter. Squadron leader James Mitchell, selected as the primary test pilot for the final evaluation flights, brought 15 years of combat experience to the program. He had flown every major British fighter type, survived the Battle of Britain, and tested experimental aircraft that pushed the limits of existing technology. But nothing in his extensive background had prepared him for the sensation of flying an aircraft that seemed to exist outside conventional physics. His first flight report described an experience that bordered on the transcendent. At 450 miles per hour, Mitchell reported, the prototype felt like it was standing still while the world accelerated beneath it. Ground features compressed into abstract patterns that flashed past too quickly for conscious recognition. The horizon curved noticeably as the aircraft's speed compressed distance into something resembling time travel. Navigation required mathematical calculation rather than visual reference, as landmarks appeared and disappeared within seconds of becoming visible. The sensation was simultaneously exhilarating and deeply unsettling. High-altitude testing revealed capabilities that defied military understanding of air combat. At 35,000 feet, the prototype could maintain maximum speed indefinitely, its engine actually becoming more efficient in the thin air that choked conventional aircraft. From this altitude, diving attacks could build velocities that approached the theoretical limits of propeller-driven flight. Gun camera footage captured during these test flights showed ground targets that appeared motionless relative to the prototype's incredible closing speed. The weapons testing program produced results that revolutionized understanding of high-speed gunnery. Traditional fighter tactics assumed closing speeds that allowed pilots time to aim, fire, and observe results. The prototype's velocity compressed these actions into milliseconds that challenged human reflexes. Pilots had to anticipate targets that would be kilometers away by the time their bullets arrived. The mathematics of ballistics became exercises in advanced physics rather than intuitive marksmanship. Yet the prototype's gunnery accuracy at extreme speeds exceeded that of conventional fighters engaging at normal velocities. The aircraft's stability at maximum speed created a firing platform more precise than anything previously achieved. Vibrations that plagued conventional fighters disappeared at the prototype's operating velocities, replaced by a smoothness that seemed to defy the violence of its passage through the atmosphere. Test pilots reported that firing the aircraft's weapons at maximum speed felt like operating a precision instrument rather than a combat weapon. Medical officers studying the physiological effects of extreme speed flight documented changes in pilot performance that had never been observed. Reaction times actually improved during high-velocity flight, as though the human nervous system adapted to the compressed time frame by accelerating its own processing speed. Visual acuity increased dramatically, allowing pilots to identify targets at distances that would have been impossible during normal flight. These adaptations suggested that human beings could operate effectively at speeds far beyond what had been previously considered possible. The psychological reports were equally fascinating. Pilots described entering an almost meditative state during maximum speed flight, where conscious thought seemed to slow while instinctive responses accelerated. Time distortion became so pronounced that flights lasting minutes felt like hours from the pilot's perspective. Some test pilots reported achieving a state of awareness that felt supernatural, as though they had transcended normal human limitations and merged with the machine itself. The prototype that Squadron Leader Wellham flew that October morning in 1944 represented the pinnacle of propeller-driven flight, achieving speeds that wouldn't be matched until jets dominated the skies. Yet this revolutionary aircraft remained forever classified, its incredible capabilities known only to a handful of engineers and test pilots sworn to secrecy. While British bureaucrats debated whether their creation was too advanced for its own good, the fastest fighter ever built gathered dust in a guarded hangar, its potential forever unrealized. The machine that could have changed the course of aerial warfare became aviation's greatest secret. A reminder that sometimes the most extraordinary achievements remain hidden in the shadows of history, waiting for the world to catch up to their brilliance.